So this class we are going to consider the inverse Laplace transform. I've sent a video already on this subject matter, but I still need to send another one to complement it because there's no way you will talk about inverse Laplace transform and you won't talk about partial fraction. And I actually explained a little bit, but I think I need to explain further because there's some part of it whereby we're going to use shifting and then translational properties. So this is just only 6 pages, so I will speak to it, and I believe it's going to help us a lot because we're going to use it when we are solving ordinary differential equation. So as you can see on the board now, we have exponential minus 3t, and then so if you find Laplace transform of exponential minus 3t, then you have 1 over x plus 3. So, and likewise, we can see that the inverse of 1 over x plus 3t will give us the Laplace transform of the main problem, of the main function f of t, which you can see on the board now, page 18 of your lecture notes. So that will give us exponential minus 3t. It's as simple as that. And you know that if you are to find the Laplace transform of t, you have 1 over x squared. Remember, t raised to power n as n factorial over x n plus 1. So here, n is 1. So you have 1 factorial, that's 1, then x, 1 plus 1, you have 2. So what is the inverse of 1 over x squared? That will give us t. Just like we have linear property for Laplace transform, we also have linear property for Laplace inverse. What do I mean by that is that, look at this question on the board. We're asked to find the inverse of everything here. So what we're going to do is this. Each of them we take inverse. It's just as if you are trying to do something like you want to expand, right? You may call it like that, but that's not really expansion. Because here, what we are trying to call, we call it linear properties. 4 over x minus 2, we take its own inverse. 3x over x squared plus 16, we take its own inverse. 5 over x squared plus 14, we take its own inverse. So that's why we obtain this. So, but the question now is this. How do we undo each of them? Look at this one. The first one is 1 over x minus 2. So this one will give us 1 over x minus 2 will give us, that is exactly exponential 2t. You agree with me? Exponential 2t. And what about x over x squared plus 16? This one will give me cos 4t because this is actually 4 squared 16. Now, what about this one? If you look at this one, x squared plus 4. When you hear x squared plus 4, denominator, that is actually talking about sign. And in that sign, you know, you are supposed to have a at the top. And if this is 4, this is 2 squared, there should be 2 here, isn't it? There should be 2 at the numerator. So if you put 2 here, definitely you come back and divide this one by 2. You get that? Let me explain again. Sine 80. Sine 80, Laplace transform of sine 80 is what? Is a over x squared plus x squared. Now, in this case now, if this is x squared plus 4, definitely 4 here, you can actually this one as 2 squared. So 2 can come up here. So by the time you put 2 at the numerator, you divide this one 2 by 2. It's just as if you put 2 at the numerator, you put 2 at the denominator, and that denominator will be under 5 here. So that is why we have this as the Laplace inverse of the problem. Now let's consider this. Remember, for translation and shifting property, Laplace inverse of f of x is f of t. The leveling Laplace inverse of fx minus a is EAT f of t. You know this before because Laplace transform of this one here of EAT f of t will give you fx minus a. So now let's use this shifting principle. Now, example 1, you have 1 over x squared plus 4, inverse of this. Of course, you can see here, by the time you have x squared plus a, you're talking about sign. So here now, this is 4. So you put 2 at the top, you divide this one by 2. That's why here now, you can see now that I put 2 here, there's 2 here, there's 2 here. So that this one will give me a squared, that is a here. So this one will give me 1 over 2 sine 2t. Now, let's now take a look at this now. Let's now say we are interested to find Laplace inverse of 1 over x minus 1 squared plus 4. Now, definitely you can see this one and this one. If you remember, sometimes ago in the class, I wanted to jump to use this kind of idea, but none of you actually followed me. Now, let me explain over again now. Sine 2t will give us this. Now, by the time you now have x minus 1, immediately that thing should come to your mind is that if you have x minus 1, that is actually exponential t. Because you are shifting away from t. So 1 over x minus 1, then square plus 4. Then by the time you see x minus 1 squared, you are subtracting 1 from x. Definitely you are talking about exponential t. So that is why we have 1 over 2 exponential t sine 2t. Actually, I would advise you don't even need to expand it, because this expansion can even confuse you. So you don't even need to expand. So from here, then you get this directly. Now let's take a look at another example again now. We have Laplace inverse of 1 over x minus 3 squared. Now, but you know that 1 over x squared is t. Laplace inverse of 1 over x squared is t. Is definitely x minus 3. It means that 1 over t, then you are shifting away, exponential 3t here. That will be minus 3. Minus 3. So as you can see here now, in this example 1 and 2, we've actually used shifting and translational principle. Now let's take a look at another fraction now. That's why I said that. I said there is no way you will find Laplace inverse and you not talk about partial fraction. Because we're going to use partial fraction to break any big fraction to small fraction. Definitely, we need some rules. So let me explain the first one now. Look at this one now. Rule number 1. If you can easily spread the denominator, you can see here now, x squared minus x minus 6. From here, you can actually see that if you multiply 6 by x squared, you have 6x squared. If you find the factor, you have 3x and 2x. So if you have 3x and 2x, definitely you know that there's a way you can handle 3x and 2x to give you x. 3x and 2x, it will give you x. So definitely you cannot see that x plus 2x minus 3. By the time you expand this, it will give us this one. So this one is as simple as that. So, but the question now is this: how do we know that 1 and 2 here? So we use partial fraction. We use partial fraction because you can't just say 3x plus 1 will give you 1 plus 2. There's a way we handle it so that we can successfully break this big fraction to small 2 fractions. Now let's take a look at this example now. Look at it now. We now want to find Laplace inverse of 3x plus 1 over x squared minus x minus 6. Look at the problem on the board. This is the same problem. I'm not asking you that I want to find the inverse of this. So instead of finding the inverse of this function that we don't know, we can find the inverse of this. And remember, if this is equals to this, if this is equals to then Laplace inverse of this, same thing as the Laplace inverse of this. So now you can ask it now. Inverse of 1 over x plus 2. That is exponential minus 2t. I think you know that one. It's very simple. And what about 1 minus x minus 3? That is what? Exponential 3t. Then you multiply by 2. So you can see now that that's all. That's all. So if you ask you to find the Laplace inverse of this, then you think of partial fraction. Then what is partial fraction? We can't use partial fraction without talking about the rules. Let's consider the rule number 1. Rule number 1 says that the power of the numerator, the degree of the numerator should be lower than that of the denominator. That is always true about partial fraction. Let me give an example now. What is the degree of 3x plus 1? The degree is 1. What is the degree of x squared minus 3x? The degree is 2. So the degree of the numerator must be greater than the degree of the denominator. As you can see, the degree of this one is 1, this one is 2. So the degree of this one must be less than the degree of the denominator, or we can say the degree of the denominator is greater than the degree of the numerator. That is rule number 1. Rule number 2 says that by the time you break it down, you find the coefficient, you find the additional parameter, additional constant, which you will see very soon now. Rule number 3 says that if the denominator is a repeated factor like x plus a squared, then definitely what you are going to have is a over x plus a plus b over x plus a squared. See, it's very simple. See, look at me. X plus a raised to power 1, x plus a raised to power 2. That's all. Now, what about if you have x plus a raised to power 3? This is also repeated root. What do you say is that you break it down by using a over x plus a, b over x plus a squared, plus c over x plus a raised to power 3. Now, what about if you have quadratic? This is the problem you can see from me in your exam. Something like this, because do I expect me to give you simple repeated root? Anyway, you can't predict, but let's just watch and see. But look at something like this now. You have something like this. If the denominator is quadratic, x squared, definitely the numerator must be of the lower power. So we have px plus q. Why do I use px plus q? Because this is quadratic, and quadratic will mean 2 roots. And that root means that I need 2 constants. That is why you have px plus q here. Now, let's take a look at the last rule now. Rule is if you have x squared plus px plus q. Look at this now. This is like combination of this rule is the combination of rule 4 and rule 5. This one here, let me show you now. This one, if you take this one, it will be divided by, let me just say, divided by this, which is the first time here, plus divided by everything here squared. Let's say that this one is 3. If let's assume that the power is 3, then it's gonna be what? Divided by x squared plus px plus q, plus divided by x squared plus q squared, plus divided by px squared plus ps plus q raised to power 3, just like this principle. This is the principle I'm using here now. I get me. The principle is if it's x raised to power 3, then over x plus a squared over x plus a raised to power 3. Now, but here, each of them is actually a quadratic. So if each of them is quadratic, definitely the numerator will be of lower power, And if it's quadratic, you need two roots. Then definitely this one will now give us Ps plus Q, and this will be Rs plus T. That's PQRS. It's very simple. If you expand this, you see that the leading power will be S to the power 4. And if it's S power, then you need 4 constants. That is why you see Px plus Q. So it's more or less as if I'm combining rule of this and rule of this. Don't worry, we'll solve an example that has to do with something like this. Let's consider example 1. We want to find inverse of this. Inverse of this. Look at this. If you look at the denominator, it's very simple. Look at the denominator. X squared times 10 will give you 10x squared. And if you have 10x squared, definitely 10x squared. 10x squared is you can use 2 and 5. 2 times 5 will give you 10. So if you put x beside the 2, then you need minus 3. Just definitely you are dealing with 2x minus 5x. So 2x minus 5x will give us minus 3x. So it's as simple as that. So if that is the case, you can now see now that we can easily express the denominator in terms of bracket like this. Because if you expand this now, x times x will give you x squared. X times minus 5, that's minus 5x, then plus 2x, then minus 10. That will give us this, which is this. So instead of finding this, it's still the same thing as Laplace inverse of x minus 19 over the 2 now. So let's proceed. What do we do now? We now say a over the first one plus b over the second one. That's how I obtain my equation 2. What is now the next step? The next step now is this. You multiply both sides by the denominator here. You multiply both sides by denominator. So by the time you multiply both sides by denominator here, everything here will come down here. That is why you can see here now. Look at it. This is the denominator. You multiply by itself. So this one will cancel this one. Then you put everything here. You multiply by here. X plus 2, x plus will cancel. So what will now remain is a multiplied by x minus 5. You put everything here beside this one again, beside b. So what you have is what? X minus 5 cancel. Then you have b multiplied by. So that is how we obtain this expression. So in your lecture note now, you can see that this one here, we cancel this one here. Okay? So what now remains is x minus 19, a into bracket x minus 5 plus b into bracket x plus. That's our equation 3. Now what's the next thing now? We need to find our a and b. How do we find our a and b? Let us set x equals to plus 5. By the time we have our x to be plus 5 here, this one will give us 0. Then you can find b. So if x is 5, 5 minus 19 will give us minus 14. This one will give us 0. By the time you put 5 here, that will give us 7, 7b. So from here, we can find our b to be minus 2. We proceed again and find the other coefficient, other constants. In this time, we need to set this one to be 0. So how do we set this one to 0 now? X, that is if x is minus 2. If x minus, this one will definitely go. So you put minus 2 here. That will be minus 2 minus 19. A into bracket minus 2 minus 5 plus b into bracket minus 2 minus. So this one will go. So then from here, you can find your a to be what? To be 3. So let's return it back to the fraction. So we now have, I'm talking about this fraction here. That is our equation 2. We know a, we know b now. So you put it down, then you have this. So Laplace inverse of the problem now is not the same thing as Laplace inverse of this, Laplace inverse of this. And looking at this one, 3 over x plus 2, definitely this is not the same thing as 3 exponential minus 2. So what about the next one? The next one will give us minus 2, then exponential 5c. So that's how to find Laplace inverse. But remember, in this case, is because we can easily express the denominator in terms of x plus 2 multiplied by x minus 5. That's all. Now let's consider another example again now. Here, look at this problem now. We are given this, we want to find the Laplace inverse of this. What do? We use one of the rules. Even not only a rule, we combine 2 rules. Here, x plus 3 is already a law. So that will definitely give us a over x plus 3. Now what about x minus 2 squared? That will give us b over x minus 2 plus c over x minus 2 squared. I'm talking about for x minus 2 raised to power 2. That will be x minus 2, then x minus 2 squared. Let me show you the rule. This is the rule. If you go back, this is the rule. Can you see the rule now? The rule is that the repeated factor x plus a squared will give you a over x plus a, b over x plus a squared. This is the rule I've just used now. So let's proceed. But don't forget the procedure is as simple as that. What's the next step now? After you have it in short, in simple fraction like this, you multiply both sides by the denominator. By the time you put the denominator here, I get it will cancel this. So what we have is 3x squared minus 4x plus 11, which is the numerator here now. Then plus everything here, you put it down here, you multiply by a. So x plus 3 that you come here, we cancel, then you now have a multiplied by x minus 2 squared. What about b? You multiply everything by here, then you now have b multiplied by x plus 3. X minus 2, we take care of one, we take care of one of this, then you have x minus 2. Then here again, you have c into bracket, you multiply by x plus 3, x minus 2 squared. So x minus 2 squared, we cancel this. So what you now have is c multiplied by x plus 3. That's our equation 2. So this is what we are going to use now. We are going to use our equation 2 to find a, b, and c. Now, it's very simple. The first step you notice is this. When our x is plus 2, this one will go. This one will go, then we can find c. Now, let's put it down. When x is 2, you put 2 here again. That's 2 squared. You put 2 here. Then by the time you put 2 here, you can now see 2 minus 2 will give you 0. That's why we obtain this 0. By the time you put 2 here again, 2 minus 2 will give you 0. Then this one will give you 0. Then this one will go. Then if you put 2 here, 2 plus 3, then you see now that by the time you expand this, you have 15 equals to 5, 6. Definitely c is equals to 3. Now let's proceed again. When x is minus 3, how do I know that I should use minus 3? It's very simple. Look at this one. By the time you take minus 3 here, this one will definitely go. By the time x is minus 3, this one will go. Then by the time this one has gone, then we can deal with the remaining. So when x is minus 3, let me reduce the screen so that we can see how we are jumping. Okay, I believe you can still see the screen very well now. Okay, so from here now, I'm talking about from equation 2, when x is minus 3. So I come back here. This is where I am. So x will be minus 3 here. So that will be 3 into bracket minus 3. That's what you have here. Then minus 4 into bracket minus 3. You change this to minus 3. Then plus 11. Then a into bracket minus 3 minus 2. Then b minus 3 plus 3. Definitely, you put this one here again. Then, so by the time you put that, it will go. Then from here, you can easily find your a to be 2. Now, what else again can we easily pick? We don't know what to pick again. We've used plus 2. We've used minus 3. Then you can pick any value. Just pick any value. But I would like to pick small value like x equals to 1. Because, you know, by the time anything you take, you put it down here. You substitute to this side. You substitute to this side again. So here in the lecture note, page 21, I use x equals to 1. So you have 3 into bracket 1 squared minus 4 times 1 plus 11. Then here you put 1 wherever you see 1 here. So you expand it successfully. Then you have your equation 3. You now see that you're having 3 unknowns, a, b, c. Remember, we already know our a to be 2. We know our c to be 3. So you return it back, you find your b to be 1. So what we are dealing with is that big fraction that looks, big, cumbersome, we can actually break it down to 2. This is a is 2, b is 1, c is 3. So you now, don't forget the rule. This is one of the rules, right? The rule says that a over x plus 3 plus b over x minus 2 plus c over x minus 2 squared. That's all. Because from here now, if you use linear property now, each of them will take inverse. So what is the inverse of this one? The inverse of this one is what? Exponential minus 3t. What is the inverse of x minus 2? The inverse is exponential 2t. What is the inverse of this one? Look at this one. You see that here, you need to use shifting principle. Because if this is t squared, this is x minus 2 squared, you are shifting away from 2. So then you know that here you are going to have exponential 2t. But what about this? If you scroll down, I said you should recall the first translational or shifting property, which is Laplace inverse of 3 over x minus 2 squared. This is the same thing as Laplace inverse of t is what? Laplace inverse of t is what? Of t, that's 1 over what? 1 over x squared. So you shift away from 2. That will give us 3t exponential 2t. So that is the Laplace inverse of this problem. You can now see now that here, there's no way you can break this one down. There's no way you can find the inverse of this without using the knowledge of partial fraction. I would advise you to pay attention to this. You will get it. It's very simple. So you have one assignment here. Look at this assignment now. It's still the same thing. Oh no. Okay, yes, it's still the same thing, but I've changed the numerator. It's still the same thing too. If you have to break this one down, you have a over x plus 2, b over x minus 3, plus c over x minus 3 squared. So you do that, then you have this. So there's one more example here. The example is this problem here. Just follow the same procedure. But here you can see now that by the time you break it down, a over x plus 1, and then for x squared plus 4, you have to use a numerator of lower power. That's how you see here, bx plus c. So it's just the same procedure of partial fraction. You find that, then you substitute back. So this is why we're going to call it a day. We are going to stop now. So in my next video, I will now start using Laplace transform to solve ordinary differential equation. Thank you very much. Thank you.